now we're coming back to some of our foundation. Right? So we're going to have Michael Lesnick. He's going to talk to us about persistent homology. Okay.
All right, thanks. Hey, everybody. So today I'm going to tell you about the optimality of the interleaving distance on multidimensional persistence modules. As Randy said, I'm Mike Lesnick, and I'm a member here at the Institute for Advanced Study in the School of Math. So today's topic is the theory of persistent homology, theoretical foundations of persistence, and in particular, the theory of multidimensional persistent homology. And I'm going to tell you about the main result from a paper of mine, the theory of the interleaving distance on multidimensional persistence modules. And this is a preprint that I posted on the archive in 2011 and recently have done a makeover of, I guess, in early February. So it seemed like a good time to tell you guys about this work. So the goal is, as I said, to describe the main result of this work and hopefully to do so in a way that's as accessible as possible to this diverse audience that we have here today. So just to be clear, I'm glad you guys find that funny. All right, so I'd sent out an abstract on Wednesday saying that the talk was going to be on something else, but I had a change of heart. So the topic is not this, but instead, we're not going to talk about weak laws of large numbers for persistent homology, but we're going to talk about theoretical foundations for formulating and proving such results in the multidimensional setting. So this work that I'm talking about forms sort of the first half of my PhD thesis, and then the second half was on this weak laws of large numbers applications. But so, okay, anyway. So what I want to do is begin with an intuitive introduction to persistent homology. So the later parts of this talk are going to sort of necessarily be a bit formal, but I know that not everybody here has seen persistent homology, so I'd like to just give you guys a sense of what it is for those of you that haven't seen it before or those of you that have seen it but perhaps are still learning the basics. So, okay, so persistent homology is one of the main tools of applied algebraic topology. And it was introduced in 2000 by Edelsbrunner, Lecture, and Zomerodian. And it's been studied and applied quite extensively since then. And I think a lot of the reason for the interest in persistent homology amongst a diverse group of researchers is that it offers a flexible framework for defining invariants of point cloud data and also of real valued functions. Okay, and we call these invariants barcodes. And a barcode is nothing more than just a set of intervals in R. So it's a pretty simple invariant, but they're useful. And what they do is they encode information about global geometric features of data and of functions in a way that's sensitive to the scale of those features or the size of those features. And I'll show you an example of that in just a moment. So just as we have Betti numbers for topological spaces for every non-negative integer ith Betti numbers, we also have an ith barcode of a data set or of a function for each non-negative integer I. So here's an example of the first barcode invariant of some point cloud data set. So this is a bit small, but I have a data set here that consists of a large sparse ring and a small dense ring, right? So there's sort of two cycles in this data set in some sense. And this is the barcode that I would get out, the first barcode. And so this, we see that we have a bunch of small intervals here and a couple of long intervals. And this one is sort of meant to extend beyond the screen. That's what this arrow means. So this long interval further to the left corresponds to this feature here, and this interval to the right corresponds to this feature over here. And these shorter intervals represent topological noise. Okay, so I'll explain to you sort of in an informal way how we get at this in a moment. So the pipeline for persistent homology is like this, and we'll return to this later and consider it more carefully. But for now, I'll explain it like this. We start with a point cloud data set or R-valued function and associate to that what I call a filtration, which is just a one-parameter family of topological spaces. And then I associate to the filtration this invariant of a barcode, okay? And so this barcode is sort of an analog of a Betti number for a filtration, okay? It sort of counts holes in the entire one-parameter family of topological spaces. Okay, so here's our data set again. And so let's explain first how we go from this to one of these one-parameter families of topological spaces. We're going to do something very simple. So for X, a finite subset of Rm, such as this guy here, taking m equal 2, let A be a real number, and then let gamma of A be the union of balls of radius A centered at the points of X. Okay? So for instance, if this is our X, then this might be our gamma A for some fixed choice of A, right? And we see we're sort of recovering some continuous object from this discrete object. And so the collection of all of these gamma A's defines one of these one-parameter families of topological spaces filtrations, which we denote Fx. Okay? And so now the key idea of persistent homology on an intuitive level is this. Not only can we compute Betti numbers of each space in this filtration individually, but we can track the holes in a consistent way across the entire filtration at once. So that's the key point. And the algebraic formalization of this idea is what persistent homology is. So this is best explained by pictures. So for instance, here we have this data set, and let's sort of go and consider this increasing family of spaces as we increase this radius parameter. So we see something like that, right? Okay, so now let me rewind again, and let's look what's happening closely here. So we increase the radius, and we see that these little holes form, okay? And then as we increase the radius a little bit more, these guys close up, and now this cycle forms. And note that as we continue to increase the radius, we sort of have that this hole lives across several indices in this filtration. And in that sense, this topological feature, this topological feature persists across this filtration. So we have this dependence of features, okay? And so eventually it closes up, and this other one forms and then goes on for a while. And then eventually, for a very large radius, it closes, okay? So we're tracking that sort of consistent information about these features across the filtrations with these barcodes. So again, whereas the ith Betti number counts I-dimensional holes in geometric objects, the ith barcode counts I-dimensional holes in filtrations, all right? And the number of intervals is just the number of holes, quote unquote. Okay, so, and then this information also specifies the birth and death index of each hole. Okay, so anyway, this is a bit informal, but this is the intuition behind persistent homology. Okay, so then here's our barcode again, and we see that this feature forms right when this hole forms, right, and then dies over here right when this hole dies. And similarly, this long-lived feature forms when that larger hole is formed. Okay, so all right, so that's the end of my introduction to persistent homology, and I hope it was clear. So any questions before I change gears? No. Okay, I hope that most of you guys have seen this stuff before. I know that this is the workshop on topology, and stuff like this gets talked about from time to time. So, okay, so moving on. So now I want to discuss distances on barcodes and their role in the theory of persistent homology to motivate the result that I'm going to present to you guys. Okay, so first I need to be clear what a distance is. So in this talk, so distance is just going to be a variant of a metric, but I'm going to use a slightly different definition. So it's just going to be a symmetric function, d, on a class X from 0 to infinity inclusive. So I allow objects to have infinite distances, and I require that this function satisfies the triangle inequality. So I have symmetry and a triangle inequality, but I don't require positive definiteness. And that's sort of for technical reasons, I suppose. And again, I allow infinite distances. So that's what these guys are. We sometimes call these extended pseudometrics, okay? But these serve our purposes well for the theory. So, okay, so there's been good progress on the theory of persistent homology of late. And so just to mention a couple of things. So there's been stability results for persistent homology, which apply in a variety of settings. We'll talk about one later on. And there's been approximation and inference results for persistent homology that tell us how to interpret in a statistical sense persistent homology invariants of data that's sampled at random from a probability distribution. And in particular, this is this thing that I was going to talk about and didn't. We have this weak law of large numbers for persistent homology, as I've taken to calling it. And this is a result that's implicit in recent work of Chazal and his co-authors. Okay, and this tells us that we can infer the persistent homology of a probability density function from an IID sample of a probability distribution with that density in a consistent way using estimators that are computable in practice. Okay, so that's in one sentence what you didn't hear about by my not giving this other talk. So, but the point is, there was a hand on my E, but it disappeared. So, so what I want to say is that all these results have in common the fact that they depend on a choice of distance on barcodes, and in particular, they depend on a distance called the bottleneck distance that we denote dB on barcodes, right? So the bottleneck distance is used to pose all of these results, okay? And in some sense, this is a talk about the bottleneck distance and its generalizations. Well, in a very real sense. So, okay, so shifting gears again, I want to say a couple of words about multidimensional persistent homology, and you'll certainly hear more later. So multidimensional persistent homology, as the name suggests, is a multi-parameter generalization of persistent homology, and it was introduced by Carlson and Zomerodian in 2006. Okay, and so I haven't said this yet, but ordinary persistent homology is being, well, maybe I did say it, but regardless, ordinary persistent homology is being applied in a lot of different places. Like there are a lot of people interested in applying it to different data arising in science and engineering, and that's, for the most part, not the case yet with multidimensional persistent homology, with a few exceptions. But I believe that that's going to change fairly soon. So in particular, I think it's interesting to understand the theory of multidimensional persistent homology as sort of a guide for how some of these applications should be developed. Okay, and I'm not going to say as much as I would like about motivation for considering multidimensional persistent homology today just because of time constraints, but just to say a little bit for now. So using multidimensional persistent homology, we can define invariants of Rn valued functions for n greater than 1, so we can enlarge the space of functions that we define invariants of. And we can also define richer invariants of point cloud data that we expect to be more robust to noise than their 1D counterparts. Okay? And part of passing from the statement that we expect them to be more robust to saying that they are provably robust in a certain sense involves having the right choices of distances to work with in the multidimensional setting. Okay? So with that in mind, we'd like to have theory for multidimensional persistence analogous to that which we have for one-dimensional persistence. But it turns out that the definition of the barcode doesn't generalize to multidimensional persistence, at least not in a completely satisfactory way. Okay? And instead, the output of multidimensional persistent homology is an algebraic object that we call a persistence module, which I'll define for you later. Okay? So since the bottleneck distance is defined in terms of barcodes, the definition of the bottleneck distance doesn't admit a naive generalization to multi-D. Okay? And, well, and sort of that's an obstacle to the naive adaptation of the 1D theory of persistence to the multi-D theory of persistence. But it turns out that despite this fact, we can formulate a lot of definitions of distances directly on n-dimensional persistence modules. So prior to this work, I know of at least 4 definitions that were defined. I'm not going to go into them here, defined in the literature. And if you start thinking about it, then you realize that, in fact, you can sort of define lots and lots of different distances. Okay? And that motivates the central question behind the research that I'm going to talk about today, which is, can we make a principled choice of a distance on n-dimensional persistence modules for use in the development of the theory of multi-D persistence? Okay? So that's I'm going to show you a lot of technical machinery later on, and it's all going to be in the service of answering this question. Okay? So my main result gives an answer in the affirmative to the question, and it tells us that a distance di on n-dimensional persistence modules called the interleaving distance is, in a certain sense, an optimal generalization of the bottleneck distance to the multidimensional setting. Okay? And it's the sort of the unique optimal generalization. So, well, this is true provided that we work with homology with coefficients either in the rationals or z mod pz for some p. Okay? And I suspect that it's also true for general field coefficients, but so far that's open. Okay? So, all right, so some distance, which we haven't defined, is optimal in some sense. So I'm going to wait till the end of the talk to define the interleaving distance. But I'm going to at least give you a sort of informal definition of what optimality is right now, and we'll formalize this later. So optimality means first that the interleaving distance satisfies a stability property generalizing the one that the bottleneck distance, or generalizing one that the bottleneck distance is known to satisfy. Okay, so it has a good stability property. And secondly, for any other distance d on n-dimensional persistence modules satisfying that same stability property, that distance is less than the interleaving distance on every pair of n-dimensional persistence modules. Okay, so here's how we should interpret this. The first property tells us that the interleaving distance is, in some relative sense, not too sensitive. And the second property tells us that amongst all distances that are not too sensitive, the interleaving distance is as sensitive as possible. Okay, so you can think of it as sort of a constrained optimum, if you like. So, okay, so then the message that comes out of all of this is, although we don't have barcodes in the multidimensional setting, there nevertheless is a good way to generalize the bottleneck distance to multi-D. And this opens a door to a barcode-free approach to developing the theory of multidimensional persistence. Okay, so that's the story without any of the technical details. Okay, so now we turn to the technical details. But maybe now's a good time for me to take a sip of water and ask if there are any objections from the audience. Okay. So, okay, into the weeds then. So I'm sort of trying to explain this stuff without assuming too many prerequisites of the audience. So there's a lot of things that I want to get through. So I'll define multidimensional persistent homology, explain the definition of barcodes quickly, define the bottleneck distance, explain stability of persistent homology as a result about persistence that I alluded to before that sort of forms part of the foundation of my definition of optimality. And I'll define the interleaving distance in terms of an object called epsilon interleavings. And finally, I'll observe that the bottleneck distance is equal to the interleaving distance in 1D. And then I'll discuss briefly the optimality of the interleaving distance. Okay, so that's the program. And oh yeah, so I want to make one remark, which is that for people that might not have seen persistent homology before and maybe don't care about some technical result in foundations of multidimensional persistence, we're still going to cover a lot of the basics that are of interest, even independent of multidimensional generalization. So that's my advertisement for the things that we're going to do next. Okay, so on to n-dimensional persistent homology then. All right, so before I go on, the thing that I need to mention is that we have a a choice in defining multidimensional persistent homology. We can either work with a Z grading or an R grading. And it turns out that, in some sense, really the right way to do things is to do it with an R grading. And that's because anything you really want to do that you can do with a Z grading, you can do with an R grading, but sometimes things get awkward when you work with a Z grading. So nevertheless, I'm going to explain things in the Z graded setting today because it'll make it easier for me to draw pictures, and it'll just sort of make notation a little bit simpler. So, or exposition. Okay, so with that said, let's get into it. So first, I'm going to define a partial order on Rn by saying that U is less than or equal to U prime if and only if each component of U is less than or equal to the corresponding component of U prime. Okay? So we have a partial order on Rn. Let's let K be a field. Now, well, let me show you the pipeline for defining one-dimensional persistent homology first. And I showed you a pipeline before, but for simplicity, I left out a step, right? So we're going to start off with a function, a z-valued function, and from that, obtain a one-dimensional filtration. And this is the part I left out. From this one-dimensional filtration, we're going to obtain a one-dimensional persistence module, and from that, we get the barcode, right? So there's this sort of algebraic step when you look at things carefully. Okay, so that's the pipeline. And in n dimensions, it's the same. Start off with a zn valued function. Associate to that a n-dimensional filtration, which I'll explain to you what it is in a moment. And from that, get an n-dimensional persistence module, and we stop there, right? So I told you before that our algebraic, our output of multidimensional persistence is an algebraic object called the persistence module. So that's the pipeline, and I'm going to walk you through it now. Okay, so there are a bunch of definitions coming, but fortunately, they're all pretty simple. So here they are. So first, an n-dimensional filtration is, an n-dimensional filtration X is a collection of topological spaces XA, indexed by Zn, and continuous injections phi x from A to B, which map from XA into XB as A and B range over Zn with A less than or equal to B. Okay, and so I have topological spaces and continuous injections. So in more mathy language, I'm just looking at a diagram of topological spaces indexed by Rn, thought of as a category with this partial order. But I'm not going to speak that language today. So never mind what I just said if it doesn't already make sense to you. But so I require that these compositions of maps commute whenever that makes sense. Okay. So these objects have a really sort of simple geometric interpretation. So, for instance, in 1D, one of these filtrations is just a diagram of topological spaces and continuous maps of this shape. Okay, so these guys are topological spaces, and these guys are injections. And similarly, in 2 dimensions, we have a 2-dimensional commutative diagram of topological spaces and continuous maps that looks like this. So, right, we have this sort of infinite lattice-shaped commutative diagram. And this is really gets us to why I wanted to work with this Z gradient, because I can draw pictures like this. Yeah?
So should this picture have diagonal maps as well, since 1, 1 is less than 2, 2 in your partial order? Or is that not? Is that
Yeah. I mean, there needs to be diagonal maps, but it's understood that that the map from here to here is this map,
right,
or any one of these maps that walks from there to there, right? That's what the commutativity condition guarantees. Thank you. So, okay, and then the higher dimensional filtrations have the same interpretation as these sort of grids. Okay? So these are the topological objects that we're looking at here. Okay, now, so what is an n-dimensional persistence module then? Well, it's really the same exact kind of object, except instead of looking at topological spaces and continuous maps, I'm looking at k vector spaces and linear maps. So I have a k vector space. So persistence module M has a vector space MA at each index A and Zn, and then linear maps just like we had before. Okay, and again, we require commutativity. So is that pretty clear to everybody? I don't think it's too much of a cognitive leap from one to the other. So hopefully it's clear. So now that we know what all of these objects are, let's talk about passing from Zn valued functions to n-dimensional filtrations. And we already saw a version of this. Well, no, never mind what I was going to say. So to pass from these functions to these n-dimensional filtrations, we consider what we call the n-dimensional sublevel set filtration. So for y, a topological space, and gamma, a function from y to Zn, and a, some n tuple of integers in Zn, we define gamma of a to be equal to the set of all little y and big Y, such that gamma of little y is less than or equal to a with respect to this partial ordering on Rn. Okay? So if n is equal to 1, then these are just the usual sublevel sets that people consider in Morse theory, for example. And for n greater than 1, these are just intersections of the sublevel sets of the component functions. Okay? That's the way you should think about this. And so if a is less than or equal to b, both lying in Zn, then it's immediate that gamma a sits inside of gamma b. And so as a result, the spaces gamma a as A ranges over Zn, together with the inclusions of the spaces gamma a into gamma b, define one of these n-dimensional filtrations. And I denote it F gamma. And we call this the sublevel set filtration of gamma. Okay, so this is how we pass from a function to one of these diagrams of topological spaces. And I thought it would be useful to show you a couple of examples. So, in fact, anyway, this is what the diagram looks like in 2D. But okay, so let's consider 3 examples. So first, let X be a finite subset of Rm, and let gamma from Rm to R. Oh, I'm cheating a little bit, by the way, because now I'm passing out of the integer valued function world to the R valued function world. But I hope you'll give me a pass on that. So anyway, we're going to let gamma of y be the distance. Gamma of little y is a distance from little y to the set X. Okay, so it's just a distance function to the set X in Rm. And so then gamma a is nothing more than the union of balls of radius a around the points of X. Okay, so the one-dimensional filtration that we get out of this is exactly the same one that I showed you in the introduction. So we can realize our sort of union of balls filtration in terms of a function. Okay, so that's one way to get one of these sublevel set filtrations. And then I want to show you a two-dimensional example also. Okay, I think maybe I'll skip the second one that I was going to say. But can I turn on the lights here? What's the secret? Is it?
It's on.
Oh, it's on. It feels dark somehow. But okay, if anybody can't see, then just let me know. Otherwise, I'll assume that everybody can see just fine. Okay, so what I want to do is, so I prepared this example for you guys. So I'm going to define a function gamma with components gamma 1 and gamma 2 from R2 to Z2. Okay, and so I want to look at what the two-dimensional sublevel set filtration of this guy looks like. Okay, so I define gamma 1 of X, this first component, to be 0 if X lies in this subset A here of R2, and 1 otherwise. Okay, so this is like a variant of the indicator function for the set A. And then I define gamma 2 analogously as a sort of same kind of variant of an indicator function for the set B here. All right? So that's my two-dimensional function. And so now let's consider the sub-level set filtration of this guy. And so I've drawn it for 4 different elements of Z2. And can everybody see okay over here? So, okay, so at 0, 0, this space gamma 0, 0 is just the intersection of A and B. It's just A intersect B. So it's the space with 2 components, okay? And then at gamma 0, 1, it's equal to A. At gamma 1, 0, it's equal to B. And at gamma 1, 1, it's equal to R2. All right? And so what's going on here? Well, so it turns out, so we could extend this diagram, right? I'm not really going to do it, but this space over here would be also R2. And the space over here would be the empty set. And this would be the empty set. And we would see that this row here would be the one-dimensional sub-level set filtration of the function gamma 1. And this row here, this column here, would be the one-dimensional sub-level set filtration of gamma 2. And notice that none of the spaces in this one-dimensional sub-level set filtration have any interesting topology. Similarly, none of the spaces in this one would have any interesting topology. So if we continue this up, we'd just get R2 again, and so on. And below here, this would be the empty set, right? But yet, when we sort of look at this 2-dimensional sub-level set filtration, we see some interesting topology. And so, right, because the intersection of A and B has topology. So to me, this suggests that this kind of multidimensional sub-level set filtration might be useful in probing the correlation of functions in a certain topological sense, right? To see where topologically functions are sort of simultaneously low-lying or high-lying. Okay, but that's not an application that people have pursued yet. It's sort of speculatively an application. But regardless, I hope it's clear what these objects are now. Okay, so any questions? Okay, so yes, this was from my first example. I forgot to show you those pictures. Okay, so all right, so now moving on. If we have an n-dimensional filtration, how do we get an n-dimensional persistence module? So this will be extremely basic for many of you, but we're just going to apply the ith persistent homology functor to the whole diagram in short. So what does that mean? Well, for any I greater than or equal to 0, the ith homology functor, hi with coefficients in a field k, does 2 things. First, it maps each topological space T to a k vector space hi of T. And secondly, it maps each continuous map F from topological space T to topological space T prime to a linear map hi of F from hi of T to hi of T prime. Okay, so because of these properties, hi induces a map, which I also denote hi, from n-dimensional filtrations to n-dimensional persistence modules. Okay, so for example, if I'm in 1D and this is my diagram, I'm just going to apply hi to every topological space here and every every continuous map here, and I get this diagram of vector spaces and linear maps between them, right? So it's simple. It's just a functoriality of homology in action. Okay, and so we call this hi of f of gamma the persistent homology module of gamma. And so now I've explained multidimensional persistent homology to you. All right, and there's not a lot to it. So and let me just remark that we can also do this for Rn valued functions in essentially the exact same way. Okay, so now, as I told you, we can go one step further in the one-dimensional case and define barcodes. So let's see how that goes. All right, so how does this last step work from going from the persistence module to a barcode? So this step is basically a consequence of a algebraic structure theorem for these Z-graded one-dimensional persistence modules. That the reference I know for this is Webb. And so I'm just going to go through this quickly just to give you guys a sense of how this works. I'm going to need a few definitions, which I'll sort of breeze through. So first, we need a notion of morphisms between these persistence modules. And you can define this for arbitrary dimensions, but I only need the one-dimensional case for this talk. So goes like this. So for M and N one-dimensional persistence modules, a morphism, F between them, is just a sequence of maps, Fi, as I ranges over the integers, such that these maps fit into a commutative diagram, this sort of ladder that looks like this with this commutative diagram that extends M and N, just like this, okay? So now the definition that I really need to state the structure theorem is that of an isomorphism, and this is just an invertible morphism. And it turns out to be equivalent to, for a morphism to be an isomorphism, it turns out to be equivalent to require that each of these maps are isomorphisms. Okay? So that's a morphism of one-dimensional persistence modules, just a ladder. And so now, so this structure theorem is going to represent an arbitrary persistence module, well, sufficiently nice one-dimensional persistence module as a sum of a very simple persistence modules, okay? And we call these interval modules. And so we say that the interval module corresponding to the interval AB, which we denote like this, I sub interval AB, to be the one-dimensional persistence module that has all zeros up until index A. And then at index A, there's a copy of the field, okay, which we called K, right? And then at every index afterwards, there's a copy of the field with identity maps between them up until we hit B, and then our vector spaces become 0 again, okay? So it's just this diagram with copies of the field and zeros in a simple way. So for instance, I01 is equal to this, right, where this is index 0, this is index 1, and so on, okay? So simple idea. And we can define infinite and half-infinite versions of these interval persistence modules analogously, okay? And so we need a notion of direct sum of these guys, okay? And this is this follows directly from the notion of direct sum of vector spaces and linear maps between vector spaces, okay? So if here are our two one-dimensional persistence modules, M and N, we obtain this direct sum of them by taking the direct sums at each index, right? So M1 and N1 direct sum is the vector space at index 1 in this direct sum, and so on. Okay, similarly for the maps. Okay, so now one more definition, and I can state the structure theorem that gives us these barcodes. So say a persistence module M is pointwise finite if the dimension of all the vector spaces in that one-dimensional persistence module are finite. All right, so this is our class of modules for which we can define the structure theorem. So now, here's the theorem. Okay, here's how we get barcodes from one-dimensional persistence modules. If M is a pointwise finite one-dimensional persistence module, then there exists a unique multiset. Multiset means that elements can appear multiple times in the set. There exists a unique multiset of intervals B of M, such that M is the direct sum of the interval modules ij, where j is an interval in this set of intervals. Okay? So we define Bm to be the barcode of M. So this is just, so Bm is just the set of intervals that indexes the interval modules appearing in this direct sum. Okay, so that's our structure theorem. So this is sort of the algebraic foundations behind this business about the holes sort of persisting across the topological spaces that I showed you at the beginning of the talk. Okay, so there's our pipeline, right? Via all of this together, we go from a z-valued function to a barcode. And so then I'll skip that last slide. So an important point to make is that Crawley-Bavey in 2012 showed that this web structure theorem actually adapts to R-graded pointwise finite persistence modules. So as far as I know, this has only been recently written down, but this tells us that this whole pipeline adapts to sufficiently nice R-valued functions. Okay, so that's what barcodes are of functions. And so now, given that we're talking about multidimensional persistence, the question arises of, well, why can't you do the same thing for multi-D persistence, right? Well, you can't, in short, and here's why. Well, barcodes describe the decomposition of a one-dimensional persistence module into a set of indecomposables with very simple structure, as we saw. Now, for n greater than 1, the set of isomorphism classes of indecomposable n-dimensional persistence modules is known to be very complicated. Okay, and so when I talk to people who haven't thought about these kinds of things before, sometimes this is unexpected to them. They say, well, like, isn't there some reasonable higher dimensional notion of this interval persistence module that adapts to several dimensions? Like, can't I represent each of these persistence modules as some kind of building blocks that maybe look like something like this? You know, so we have some sort of contiguous regions where the field is k and then everything else is 0. Some kind of staircase of copies of the field k where everything else is 0 outside of it. Okay, I hope it's clear what I'm talking about. All right, so something like this, where maybe everything that I haven't drawn, maybe I can represent every multidimensional persistence module as a direct sum of something like this, and then the barcode for multi-dimensions should be some object like that. I mean, some set of objects like that instead of these one-dimensional intervals. And what I'm telling you is that doesn't work, okay? And the reason is because the indecomposables are complicated. There's lots of things that might have vector spaces with multiple dimensions that don't decompose into these guys. Okay, so that doesn't mean that you can't do anything barcode-like for multidimensional persistence. So there's a couple of ideas out there for what you might be able to do. So I'll discuss them very, very briefly. So in their first paper on multi-D persistence, Carlson and Zomerodian suggested to use as a stand-in for the barcode the ranks of all the linear maps in the n-dimensional persistence module. And if you think about it a little bit, you'll see that that's equivalent to the barcode in one dimension. Okay, so for one-dimensional persistence, this reduces to the barcode. Now, in 2 dimensions and higher, you throw away a lot of information in the persistence module by looking at this guy. But still, what it has going for it is that it tracks topological features that sort of live a long time in the filtration, which is sort of the business of persistence. And Bersini and his co-authors have pointed out that this turns out to be equivalent to considering some 2n-2 parameter family of barcodes of one-dimensional slices of the n-dimensional persistence module. Okay, and I don't want to go through why that's true, but if anybody's in the room that works on applications and thinks that maybe one day they want to use multidimensional persistence, this is worth keeping in mind, especially because if n is 2, then we have a 2-parameter family of barcodes. That's somewhat of a manageable object in principle. Okay, so and then we can also consider minimal presentations of n-dimensional persistence modules. I don't want to bother going into what that is right now. But so none of these is a perfect solution as a barcode. Each has advantages and disadvantages. These throw away information. These don't, but they're not isomorphism invariants. And that's a problem in of itself. Okay, or a limitation, I should say. Okay, so given that there's no great choice of a barcode, rather than define a distance on n-dimensional persistence modules in terms of a generalized barcode, as I said, we take a barcode-free approach. Okay, so moving forward then. So let's turn to discussion of the bottleneck distance and also stability of persistent homology. Okay, so finally we're going to define this guy. So again, this is a distance between barcodes, and therefore it'll be useful for us to keep in mind for later that it induces a distance on one-dimensional persistence modules. Okay, so what is this guy? Well, I'm going to define it informally first and with an example. Okay, so informally, well, let's look at an example of barcodes first thing before we even consider what this definition is. Okay, so I'm gonna draw this example of barcodes. Okay, give me 1 second. Okay, so barcode A consists of 3 intervals, which perhaps I'll use colored chalk for this. So the first interval is 1, 6. Second interval is 2, 3. And the third interval is 0, 1. So this is barcode A. Barcode B is given by 0, 7 and 1, 4. Okay, so here are my barcodes, and so informally then the bottleneck distance between these guys is the maximum amount that I need to deform the endpoints of intervals in A in order to transform A into B. Okay, so before giving you the formal definition, just note that, say, let's look at A, and if I take the left endpoint of A and sort of move it to the left by 1, and take the right endpoint of A and move it to the, of this interval in A rather, and move it to the right by 1, then this interval becomes the same as this purple interval down here. Right, so I've color-coded these guys to indicate which intervals I'm going to match up. Similarly, if I take this magenta interval here, extend it by 1 on the left and the right, then I get this interval down here. Okay? Now, this interval doesn't match to anything, but I can sort of deform it inwards by 1/2 and sort of deform it down into nothing. Okay? And so by making these transformations, I've transformed this barcode into this barcode by moving endpoints by a distance of at most 1. All right? And so the sort of, for the optimal strategy, the maximum distance that I have to move in endpoint is the bottleneck distance. Okay? So, yeah.
So couldn't I stretch the short pink barcode to the long purple barcode? And then
Yeah. So
the purple one to the short, medium-sized pink one? That'd be more net distance?
Yeah. So, right. So I've shown one strategy for transforming this barcode into this barcode. And that barcode is associated with a cost. Right? In this slide, it's this cost C. Well, never mind the slide. But there's some cost associated with this strategy for transforming barcodes. And so I sort of take the bottleneck distance to be the minimum cost over all strategies. Okay? So anyway, maybe in the interest of time, I'll skip over the formalities. But anyway, there's a few lines of mathematics that needs to be written down, but it's simple, and that's the idea. Okay? Does anybody want me to explain this in more detail, or are we fine? Okay, Vidit desperately doesn't want me to, so we'll defer to him on that. Okay, so I mean, this talk is extremely slow for Vidit because he's an expert, so we should have warned him. But okay, anyway.
Your abstract at the last minute to sucker me in.
You had 2 days, so we can hash that out later. All right, so now we're ready. Now that we know what the bottleneck distance is, we can talk about stability of well, we can talk about the stability theorem that I told you I was going to talk about. But first, we're going to define. Well, actually, we're going to define stability of distances on n-dimensional persistence modules more generally. Okay, so first we need a distance between Zn valued functions. So for x a topological space and gamma 1 and gamma 2 functions from x into Zn, let the distance d infinity between gamma 1 and gamma 2 be the supremum over all little x and big X of the L infinity norm of gamma 1 of little x minus gamma 2 of little x. Okay, so this is our distance on functions that we want to work with. Okay, and so I don't know if there's anything else I want to say about it. It's a pretty straightforward distance, but okay, I'll leave it at that for now. So now I'm going to define a definition that will be unfamiliar to some of you, even those of you who know about persistence. So I'm going to say that a distance d on n-dimensional persistence modules is stable if for all non-negative integers I, topological spaces x, and gamma 1 and gamma 2 from x to Zn, such that their ith persistent homology modules are pointwise finite. The distance between these ith persistent homology modules with respect to this distance d is less than or equal to this distance d infinity of gamma 1 and gamma 2. Okay? So this is, it says that the distance in this with respect to d between the persistent homology modules of these functions is always bounded above by this d infinity distance between the functions. So that's what it means for distance to be stable. It's this relative notion of stability that depends on persistent homology. Okay, so now this is one of the main results in the persistence literature, worth taking special note of. In the case n equals 1, this bottleneck distance is stable. Okay, so in this case, these are functions into Z. It also holds for functions into R. Okay, so this is due to Cohensteiner and Edelsbrunner and Harrer in 2005, and in the more general form, which we need to state it as I'm stating it, is due to Chazal and his co-authors in 2009. Okay, so that's stability of persistence, right? So having explained to you stability of distances and shown you this property, I now can never mind what I was about to say actually. So just to get, I want to show you an example before moving on. So here's two functions, two R-valued functions on R, or the graphs of them rather, and this is meant to demonstrate. Well, in this picture, we have that the d infinity distance between these two functions is small. Right? There's a lot of small changes, but none of those changes are very big. Okay, and then this is these are the barcodes that we'd get out of, plotted them vertically this time, right? But you see this red function has two modes, and correspondingly we get two features, and then we're looking at zeroth persistent homology, and we sort of get a feature that lives on. And then here we have the same barcode, but with a little bit of small scale noise. small scale noise that comes from these little bumps. All right, so in the bottleneck distance, you can squash all these guys down to nothing, and so these guys are close together. So that's an illustration of the stability theorem in action. Okay, so now, anyway, I'm running low on time, so I'm gonna skip these remarks on stability. Just the main thing I want to tell you is that this result is useful. This is sort of at the heart of what this is at the heart of why the bottleneck distance is useful in the theory. Okay, so now finally, having explained stability of a distance on n-dimensional persistence modules, I can state my optimality result precisely to you. Okay, so we're going to say that a distance d on n-dimensional persistence modules is optimal if, first, this distance is stable in the sense I just defined, and secondly, for any other stable distance d prime on n-dimensional persistence modules, d prime is less than or equal to d. Okay, that's optimality. That's the definition of optimality that I work with. And so then the theorem is that di is optimal as long as the ground field that I chose is the rationals or z mod pz. Okay, so what's left? Well, I still haven't defined this this interleaving distance yet, right? So I need to. That'll be the last bit. We're going to define this distance, okay? And I'm gonna do it quickly, I hope. Okay, so again, this interleaving distance depends on a notion of interleavings, epsilon interleavings, which I'll now define for you. All right, so this definition is due to Chazal and company in 1D in 2009, and turns out to extend readily to n dimensions. So this definition will proceed a little bit more quickly than some of my others, I hope, but one preliminary definition. So for epsilon, an integer, let epsilon with an arrow symbol on top of it, which I'll call the vector of epsilons, be the vector in Zn whose components are all epsilon. Okay? Now,
So you intend that epsilon's going to be small and positive, so maybe really sort of we should think of it as a positive real number.
So I'm making a point of working in this integer graded case, and so it's fine for me to work with an integer here. But as I said, like really, you want to think of all this stuff as generalizing to the R graded case. So yeah, ultimately you can work with a real epsilon, but I'm not going to do that right now. So okay, so now so what are epsilon interleavings then? Well, we say that two n-dimensional persistence modules M and N are epsilon interleaved if there exist two sets of linear maps. First, maps FA from the vector space in M at index A to the vector space in N at index A plus vector of epsilons, as A ranges over all n tuples of integers. And then symmetrically, maps GA from the vector space in N at index A to the vector space in M at index A plus vector of epsilons, as A ranges over all n tuples of integers. And we require, I'm going to allow myself to be a little bit informal here, but we require these maps and their compositions to commute with the transition maps, these sort of internal maps in M and N, wherever that makes sense. So everything commutes that could commute. Okay? That's my definition of epsilon interleavings. Okay? And this is sort of, I don't usually write it down like this, but this is sort of a, you can write this down in terms of module homomorphisms and functors and stuff, but this is an accessible way to define it. And so when we look in low-dimensional cases, we see this really amounts to the existence of some nice-looking simple diagrams between these guys. So, so for instance, let's look at the one-dimensional case. So in 1D, M and N are zero interleaved if and only if there exists one of these ladder diagrams with each of these maps Fi in isomorphism. Okay, and I already told you before that that's the same as requiring that these modules be isomorphic, right? So M and N are zero interleaved if and only if they're isomorphic. Okay, that's not that exciting, but things are more fun when we move to one interleavings. So in 1D, M and N are one interleaved if and only if there exists a diagram that looks like this. Okay, so these maps that go down and to the right are the maps FA, and the maps that go up and to the right are these maps GA. Okay, and they have to fit together into a commutative diagram. All right, so that's what it means to be one interleaved. Now, to be two interleaved is analogous, except now the maps sort of go twice to the right before crossing from the top to the bottom and vice versa. So, and so on, right? And so now you can also give a sort of geometric interpretation of what it means for interleavings to exist in higher dimensions. And I wanted to draw a wild diagram in 2D that showed you this, but I ran out of time. So, no. So, okay. So let me go back to the definition. So, an epsilon interleaving is a pair of sets like this, right? So, I mean, I know you know the language, so just in more sort of.
I just want to know if the FA and GAs had to be isomorphic. They can just be arbitrary.
Oh no, yeah, they're not. They're just. They're not isomorphisms.
The squares have to all commute, like everything inside must commute, even though they're not isomorphisms.
Yeah, it's sort of like this gives you a sort of weakened notion of isomorphism between modules. But yeah, but you want to know if there are isomorphisms on the vector space level. The answer is no. Okay, sorry, I'm getting ahead.
Isomorphisms after a sort of double epsilon shift.
No.
The composition.
What?
First do one of them and then do the other.
Yeah, then it's not an isomorphism necessarily. It's just equal to the transition map inside of the module.
Yeah.
Okay, so, all right, sorry, I skipped ahead. All right, so I'm going to, these are the last few slides here now. So, okay, so now that we've defined epsilon interleavings, we finally defined the interleaving distance, you know, and we had to build up a lot of machinery and language to get up to this point. But here's the definition. So we define DI, the interleaving distance on n-dimensional persistence modules, by DI of M and N is the infimum over all epsilon greater than or equal to 0, such that M and N are epsilon interleaved. So this is the smallest epsilon, so that these guys are interleaved. In the z-graded case, we can take this to be minimum, I suppose, at least when these distances are finite. But that's the definition looks exactly the same when we work with real gradings, like this. Okay, so this is a distance on n-dimensional persistence modules. And so again, yeah. All right, so now, so the last thing we need to say is that this bottleneck distance is actually equal to this interleaving distance in this one-dimensional setting where they're both defined. Okay, and that's not immediate. So the way one proves this is that they show that the bottleneck distance is less than or equal to the interleaving distance and vice versa. Okay, so this direction was proven in 2009 by Chazal and company in the same paper that introduced epsilon interleavings. And so this holds for pointwise finite one-dimensional persistence modules. Okay? Then the converse direction I proved in 2011 in the first version of this paper. And then subsequently, proofs have also appeared by Bottleneck and Scott and Chazal and co-authors. And so Bottleneck and Scott call this result that the bottleneck distance is equal to the interleaving distance the isometry theorem. And I sort of have taken that name on myself. Okay, so it's worth noting that the sort of more innovative, harder, and more useful direction is this one. Okay, this actually originally in the generality I wanted it. This required some technical work, but now that we have this structure theorem of Crawley-Bavey, it's really, I don't want to say trivial, but it's like, it's pretty, you might as well say that it's trivial. So.
What is vector space? Why can't we be working with general modules at this point?
What is what?
I mean, you said we had to work with vector spaces.
Uh-huh.
Why can't we be working with general modules?
Yeah, you can define all of this in in that kind of generality. In fact, my optimality result should hold for z coefficients instead of,
The Crowley-Baby theorem does not say anything about module value, like z modules. It
Yeah.
only works or fails if you want to use it. You have to step away from z.
yeah, good point. But I was interpreting your question as being about defining the interleaving distance. But yeah, like as regards this slide, bottleneck distance doesn't make sense for general modules,
But
right?
the
For
interleaving difference.
yeah, the interleaving distance is very general. You require no finiteness conditions on your persistence modules. You don't need field coefficients. So it's nice in that sense. I mean, that really suggests that the interleaving distance is sort of, in some sense, the more fundamental object, right? But this is the more concrete object. Okay, so now I'm over time. So let's wrap up. So now we know what the interleaving distance is, and we have this optimality result for it that I explained to you. So I'm not going to really talk about proving it, especially not now, but I'll just comment that the stability result is an easy exercise. You could do it before you left the institute today, if you're leaving. But it's this property too that is really the one of substance, and it requires the way I've proven it requires giving a characterization of epsilon interleavings and some sort of constructive arguments. But the characterization is the most interesting step. So to
DI is still, sorry to keep interrupting.
that's fine. That's fine.
But, so you're saying DI is continuous, right?
I mean, like.
The way you've given it is just a continuity statement. You choose the right metric on the space of functions, you choose the right metric on the space of persistence diagrams, and now you have a continuous map.
Yeah.
So one.
Yeah.
Okay.
Yeah, sure. Okay, so to finish up, so the upshot of all of this is that this optimality result shows that this interleaving distance behaves well with respect to the persistent homology of Rn-valued functions, and it motivates the use of DI in the development of theory of topological inference. Okay, and so as I said in the intro of the talk, in my PhD thesis, in the second part of it, I used the interleaving distance in generalized interleavings to develop two-dimensional analogs of this weak law of large numbers result that I've mentioned several times. And so that's one application of this kind of machinery, and so hopefully there will be more in the future. So anyway, that's all. Thanks.